Okay, lecture 59, hypothesis testing for difference of variance or standard deviations examples. In what follows, we will assume that the initial population are both populations are both normally distributed. It's really important for that. If one of them other is not normal, the results are not trustworthy, even if we have a good sample size. So for what we're doing here, we're assuming that we have normality of the original data. Okay. Example 1, we will test the claim at the 5% significance level that the standard deviations of men's and women's heights are equal. All right, well, we know that men's heights are normally distributed and women's heights are normally distributed, so we're good to go. Okay, so we're going to test it at the 5% significance level, alpha equal 5, sorry, that's a sigma, sort of a sigma. Alpha, the significance level, is 5%, which is of course 0.05. And what are we testing? We are testing that the variances are equal. So of course H naught is that sigma 1 is equal to sigma 2. The problem here is that I say that what we're testing is that they're equal, which means that the alternative hypothesis is sigma 1 is not equal to sigma 2. Really, isn't it? If I'm making a claim that they're equal, that's the null. The alternative isn't that one is greater than the other, it's that they're not equal, all right? So we have a little bit of a snag, maybe because I just got done saying in the last lecture that we want to always be doing a right-tailed test. Well, this is two-tailed, so what are we going to do about that? The answer will come to us, so you probably already kind of know what we're going to do, if you remember from last lecture, but it'll come to us if we just kind of push forward here and see how to think. So leave a little room in this space, because I'm going to write something else over here, but we're going to come back to it. Okay, so we take a sample of size 12 of men and compute the I'm not using very big sample sizes just because I don't have a lot of room to put up a lot of tables. So I'm just using some small sample sizes so we can just get parts of the table up that are easy to see and good enough for example's sake. Okay, we take a sample of size 12 of men and compute their weight sample standard deviations to be 27 pounds, and a sample of size 16 of women and compute their weight sample standard deviation to be 32 pounds. Sketch the probability curve showing the critical value and rejection region. All right, so let's put the curve down here, kind of generic F curve. All right, now we learned some things there. We learned that from the sample of men, the standard deviation was 27 pounds. From the sample of women, it was 32 pounds. That tells you right there that we are using women as population 1 because the sample standard deviation turned out to be bigger, right? All right, that helps me figure out what my F random variable is. It's degrees of freedom 1 and degrees of freedom 2. The degrees of freedom 1 go with population 1. What was the sample size drawn from there? And the answer is go look at the sample size for women, right? Because that's population 1. So, you know, you can kind of maybe squeeze in here. Pop 1 equals women. Pop 2 equals men, right? All right, so the sample of women had that had the largest sample standard deviation, and it was size 16. So I'm going to look at 16 minus 1 equals degrees of freedom 1 is 15. And for men, the sample was size 12. 12 minus 1 is 11. So I'm looking at F 1511, ain't I? All right, and I want 0.05 significance level. And of course, the way we always do this, we don't have a symmetric curve, right? The chi-square curve is not symmetric. The F curve definitely isn't. So we're not symmetric about the hump. So we're not, you know, you can't get one region and fold it over to get the other. But we can just say kind of generically, we can draw it in here. I want half the area here and half the area here. So I want 0.025 here, and I want 0.025 there, right? Okay. Now, like I said, most tables don't give you this value. It's a little hard to figure out. They'll give you the right value for right-tailed probability, and that's all we're going to need, as we'll see here. So I guess I'm ready to say the following then. We have set it up, have we not, so that we are going to get the larger of the ratio. We've set it up so that, because I guess I have not said explicitly yet that our test statistic is, I'm going to go ahead and put it over here. The test statistic. Here is our test statistic. I think I mentioned it last time, but it's always S1 squared divided by S2 squared, right? It's always a sample standard deviation, or sample variance divided by the other sample variance. But for our purposes here, we just, like I said, retroactively label things so that we're always talking about this being the bigger number. Once we do that, we're not even allowing the possibility that this ratio gets small. So what we've effectively done is we have taken our two-tailed test and we've purposely rigged it so that we'll always end up in the right tail. You can do this with anything. If we were looking at the difference of two means, right? You know, if we wanted to, if we had mu1 equal mu2 was h0, you don't have to write this down, but just watch what I'm doing. And h1 was mu1 does not equal mu2. Well, what's the test statistic? The test statistic is to look at x1 bar minus x2 bar. Well, there's other stuff involved, but the numerator was this, x1 bar minus x2 bar. Now, that's going to be negative if that number is smaller than that number, but I could just as easily flip it around and look at that test statistic, and then it would be positive, right? So all I'm doing, I just relabel which one is x1 bar and which one is x2, which one is sample 1 and which one is sample 2, which one is population 1 and which one is population 2. It doesn't matter how I label them, correct? So for a two-tailed test, I'm either going to get a positive or negative difference here. Well, let me just always rig it so that I get the bigger one minus the smaller one. That way, which tail am I in? I'm not in the tail that gives me, you know, small numbers or negative numbers in the case of a mean. I'm in the tail that gives me bigger numbers. I'm doing the same thing here. I am rigging it so that this test statistic won't lie. If it's going to lie in a tail, it won't lie in the tail for smaller values. It'll lie in the table for larger values. That way, all I really have to do is convert, you might say, to alpha equal half of what we were doing, 2.5%, and do H1 being sigma 1 greater than sigma 2. So now it's right-tailed. Right-tailed. Right, so that's just a little trick we do. We just make sure that whichever extreme we get, we always set it up so that we're always getting over here, then that way we can use the table. All right, that's all there is to that. Anyway, so let's go on. I have that, what is the test statistic then? It is S1 squared over S2 squared, which is 32 squared over 27 squared, and I get about 1.4, all right? And, oh, I didn't even get my critical value here, sorry. So if we, it's probably pretty cluttered here, but we're now using alpha equals 0.025. Can we get it here? We're looking at 15, so we go over to the top as 15, and then there's 11, so it comes over here. Is that what I get? I think I get this one. Oh yeah, I think my label, this label actually goes for this stuff over here. So if you go down here, it's this one, 3.3299. 3.3299. Well, my test statistic was over here, probably more like over here, I don't know. Definitely in the non-rejection region, not out here in the right tail. We've rigged it so that we'll either be in the right tail or we won't be we won't be rejecting it, right? So it's either a rejection here or not at all. So it doesn't land in there, so we failed to reject. So at and now it's still alpha equal 5% significance level, because that was what the original problem was. We just mechanically cut it in half, so we just had to look at the right tail. But it's at the alpha equal 5% significance level. There is, and what happens if I switch? Less squeak maybe? There is insufficient, not really, evidence to reject the claim that men and, I guess, men's and women's weights have different standard deviations. I am abbreviating so that you don't have to hear the squeaking. So I'm sorry, I still have my table up. Let me get rid of that. There we go. Okay. There is insufficient evidence to reject the claim that men's and women's weights have different standard deviations. Okay, so that's basically it. We're not again claiming that they do definitely have the same standard deviation, but I'm sorry, it was just a claim that it's the same. Forgive me. There's insufficient evidence to reject the claim that men's and women's weights have the same, yikes, standard deviation. Okay, we're not saying for sure that they have the same standard deviation. Of course, we're just saying that we don't have good enough evidence to believe that that they are in fact different. All right, let's do one more. You can read the next one on the next page while I rub this out. I didn't put the outline in, I just put the problem there. And let's see, you get at least this much right here rubbed out. Okay. Your company produces a small scale people use to weigh food portions. Two processes, process A and process B, have been developed for manufacturing these scales. And you'd like to know which process results in scales that are more consistent in their weighing, that is, results in a scale population that has a scale weight population that has a smaller variance. You take 10 scales that have been manufactured according to process A and record each of their readings when weighing an object that is exactly 8 ounces. Their various weights, 8.2 ounces, 7.93 ounces, etc., have a sample variance of 0.0015 ounces squared. You take 10 samples, 10 scales that were manufactured using process B and do the same thing, and you arrive at a sample variance of 0.0018. So immediately, population 1 goes with process A, population 2 goes with process B. Excuse me. Turn that around, right? Population 1 goes with process B because they have the larger standard, larger variance. Population 2 goes with process A because that is the smaller variance, all right? And so we have S1 squared equals 0.0018 and S2 squared equals 0.0015. We can now label them because we know which is bigger. Test whether process A produces a smaller variance in weighings of an 8-ounce object. So you're kind of hoping or thinking it's process A, but you don't know. So the null hypothesis, that no, that's not the case, that there's no difference, is that the variance of one is equal to the variance of the other. What is the alternative hypothesis? Well, we are now rigging it so that the larger sample came from what we're calling process 1. So it's, you know, sigma 1 squared is greater than sigma 2 squared, and we will be doing a right-tailed test. Right-tailed. Okay, so I say go ahead and I don't say it, I just have it out here that we should do. I'll draw the generic picture, right-tailed here, and we are testing it at the 0.05 significance level. So this time I really do want 0.05 area in that right tail because it starts off as a right-tailed test. It wasn't a two-tailed test that we cut in half, right? It really went alpha 0.05 right there. And F is what? Well, both samples are of size 10, 10 scales. So we take 10 minus 1 and 10 minus 1, we're going to get F9, 9. Okay, let's look that up. See if we can see this through all our mess. Here is 9, and it goes down to 9, and I do, well, okay, let's see. 9 and 9 is 4.0260. Oh, that's because I'm on the wrong table. See, I'm on 0.025. I want to be on 0.05. Whoops, wrong one. We never used that one. 0.05. Here we go. Go down to 9. Yeah, 3.1789. That is what I have. 3.1789. All right, there's my cutoff value. Let's compute the test statistic, which is the ratio of sample variances, where we put the larger one on top. So there's the test stat. There it is from the previous problem. I'm going to erase it just to rewrite it. So notice how what we're testing in this one is variances, whereas before we tested sample standard deviations. Doesn't matter. The test statistic is the same. So the test statistic, always when we are testing equality of variances or standard deviations, our test statistic is sample standard deviation that is larger divided by the sample standard deviation that is smaller, and we get 0.0018 over 0.0015, which works out to be 1.2. All right, so that's, over about here somewhere, right? Definitely in the non-rejection region. So again, just worked out that we failed to reject. That doesn't always happen when you're comparing variances or standard deviations, just in these two examples it did. All right, so what is the final conclusion? At the 5% significance level, I'd really appreciate if you'd write the words all out. And again, let me get rid of my background here. There, sorry. At the 5% significance level, please write it all out. I'm just abbreviating so that you don't have to listen to the squeaks. In fact, let me try another marker. Let's see what this one is. At the 5% significance level, there is insufficient evidence to reject the claim that the variances are different, are the same again. Here are the same. Getting dangerous there. I'm saying exactly the opposite of one. The variances are the same for the different processes, right? The different processes for producing the scales. So, why is this a value? It may be that process A was a little more expensive than process B. But if it gives us a lower variance, then that might be a reason to go for it, right, to use it. But we don't have strong reason to think that it does here, right? So based on this test, we wouldn't recommend abandoning process B and going to process A because we don't really have good evidence to believe that it has a smaller variance. Of course, again, because we've set it up so that we have, here's the variance for process B divided by the variance for process A, the ratio was 1.2, which is a little bigger than 1. So, that suggests that maybe process A has a smaller variance overall. But we don't have enough information. It's not enough bigger. It'd have to be way out here past this 3.1789 before we'd go, oh yeah, given our sample sizes, we really do think there's a good reason to go with process A. It really does look like the variance is smaller there. But as I've said before, when you get something like that, you might go, hey, maybe there is something going on. So of course that suggests to try it again with bigger samples, right? With bigger samples, we can often move things out into a rejection region that we wouldn't otherwise have been able to, like we didn't here. So we would say that the difference is not statistically significant for these sample sizes, but maybe getting bigger it would be. So you would probably go to your boss and say, yeah, I think we should test, 100 and 100 instead of just 10 and 10, right? Okay, we'll stop here. Thanks.